Hi, everyone. Yeah, brilliant. We can get started. Thanks, everyone, for being here. My name's Fawcett. I've worked at IBM for 10 years now. Spent 10 years working on storage. And I'm here to talk to you today about the performance improvements we're making for Erasure coding. So before I get into the motivation for it, quick disclaimer. So the improvements that we are making here that I'm going to show, they are in varying states of completion. So some of them have already been merged into main, some are at the pull request stage, and other ones are still in the prototype stage, so they're not quite ready for review. Okay, so why Erasure coding? So Erasure coding has a lower total cost of ownership than replication. If you look at the example I've got here, we have a 4+2 Erasure coding. So you can see here we have taken a data object and we've split it into 4 chunks, and then we generate 2 parity chunks from the object, and that way we can rebuild the data if any of the data chunks are lost. So if you look at the overhead, the 4+2 only has a 1.5 times storage overhead. So if we have 1 terabyte of data, we need 1.5 terabytes of storage, but the 3-way replication is double that. Despite the fact that it has such a lower total cost of ownership, the performance isn't quite there to convince people away from replication. Telemetry shows that the majority of people are still using replication. So before I get into the nitty-gritty with the code, I'll show you what I've done to the test tools first. So the first one I want to show off is the offline consistency checker. So this is a Python utility we've written, and it's essentially an interface over some existing Ceph utilities, namely the object store tool and the Erasure code tool. So how it works is, first we take the OSDs offline in a given pool. So in this example, again, I have a 4+2 EC pool. There's going to be a common theme through this. All the examples are 4+2. So yeah, we take the OSDs offline. We use the object store tool to read back all the data chunks and the parity chunks. We combine the data chunks together, so we have the full object. We then run that through the Erasure code tool to generate the parity chunks, and then we compare them to the data we've read off the OSDs. If they match, great, happy days. If they don't match, then it means we've got a problem. It means one of our enhancements has gone awry. So this kind of tool, we think it's great for running at the end of a test. So if you have a test where you're driving lots of I/O to a pool, and you want to check that everything's consistent at the end, then you can just set this tool off, and it will go and check the pool for you, and you'll get a nice printout at the end. It also exists as a tautology task, so it can be ran at the end of a tautology test. Next, I'll move on to the I/O exerciser. So there is existing I/O tools within Ceph, such as RBD Bench, and I know there's third-party tools as well. We found it quite difficult to sufficiently stress test the Erasure-coded pools with the existing tools, so we went ahead and made our own. The new exerciser generates sequences that better test boundary conditions than the tools we had available, and we can also generate redos requests for multiple reads and writes. Because it exists as a set of C++ classes, we can integrate it easily with other tools and vice versa, and that leads me on nicely to the next one. So this is an online version of the tool I mentioned before, the offline checker. The difference with this one is that it doesn't actually rely on any existing tools, and it's a set of C++ classes, and we don't need to bring the OSDs offline. So this means that we can then integrate this tool with the I/O exerciser and other tools. And if you have, for example, you have a test where you're doing a lot of different overwrites to an object, or you're moving an object around and you want to make sure that it's consistent at every step of the way, we can then do that without taking the OSDs offline and impacting the test. I think that's it for test tools. So I'll talk about the read path next. So in order to show off the changes we made in the read path, I'll first show an example of a read today in the squid release. So in this example, again, we've got a 4+2 EC, and we just want to read some of the blocks on the A data chunk. But what actually happens today is we need to go and read the entire data stripe. So we need to read from A, B, C, and D, and then most of that data is just getting discarded, which isn't very good. That's generating a lot of unnecessary I/O and network amplification, which slows things down a lot. So we can do better than this. The next step on is what we're calling a partial stripe read. So again, we just want the blocks on A, just a subset of the data chunk A. And this time we can actually just read the entirety of A, and then we just return the blocks that the client has requested. This is already much better, and it reduces a lot of the network and I/O amplification and speed things up a lot. But we can do a bit better still. You can skip that. Yeah, so for this one, we're calling this a minimum required read, and this is where we will just actually return the exact blocks that have been requested by the client. I will move on to the write path next. So again, I will show an example of a write in Squid today. So in order to do a write with Erasure coding, we have to first read back the data, because we are going to need to combine our new data with the old data and generate the parties from it. So what's happening here is, even though we only want to overwrite again a small set of the blocks on A, we need to read back the full stripe. We then combine our new data with the full stripe that we just read, and then we write everything back, including the parities. So again, really wasteful here. You might think that the next one, you might have clocked on that the next one's going to be a partial stripe write, is what I'm going to show. But for the sake of brevity, because it's a lightning talk, I've skipped that out and I've just went straight to the final optimization that we're going for. And this is a minimum required write. So here, again, we want the same blocks. Instead of having to read the whole stripe, we instead just have to read the equivalent blocks on the chunks that we are not writing over. So in this example, it's the equivalent blocks on B, C, and D. We then use those blocks that we've read, and we combine it with our new data to be overwritten, and we can generate the parities from that. And then when we're writing back, we are just writing back the exact blocks on A, and then the exact blocks on parity 1 and parity 2. The observant among you might have noticed that the chunk size in all these examples is 64K. So the reason for that is that, well, so the default chunk size today is 4K. We think that these improvements are going to pave the way for us to increase the chunk size. A larger chunk size will give us better performance of large IOs out the box, and we think that these improvements will also give us the performance enhancements on smaller IOs as well, so we can get improvements across the board. So this is an interesting one that we found. We found this in our profiling. So if you think about a write today, if a write comes into the primary OSD, and then some data has to be written to the secondary OSD, then the primary OSD has to send that across. So what it does is it just puts the data in a buffer, and it encodes it and sends it across. But we have a problem because we have pre-appended information about how the data is laid out first. The length and the structures and all that stuff, they get stuffed in the data buffer. When the message is sent across to the other end, and the secondary OSD tries to decode it, because the data is no longer aligned, it has trouble decoding it, and it has to move the data around. This results in a really nasty mem move where the entire data buffer is being copied. So we have come up with a fix for that. So instead of having one buffer now, we have two buffers. So we have a payload buffer, and that includes all the information about the data itself and the structures and the length. And then the actual raw data itself is just included in a buffer alone. And that actually improves things a lot. I can show you an example here. So I've got two flame graphs here. If you're not too familiar with flame graphs, all we really need to worry about here is that the length on the x-axis of the different blocks show how long we've spent on the CPU. So on the left, you can see we have this big plateau here with the mem move at the top, and that's the data being shifted around in the secondary OSD. And then with our fix in, you can see you can't even see the purple highlighted anymore because we've completely removed that plateau. I think in this profile, the plateau was about 8% of the CPU time for this particular profile. So with big improvement there. The last one I want to show you today, reduction of metadata updates. So what we have here is I've got a full stripe write, and on the full stripe write, I've shown that we have two lines going to each data chunk. The blue line represents the data that's being updated, and the green line represents the metadata that needs to be updated in the chunk, things like version and stuff like that. So this is fine for a full stripe write because we're writing to everything. But if you think about the partial write optimization, it's not so good because even though we're in this example only writing data to one of the data chunks and the two parity chunks, we need to update the metadata for every single chunk in the 4+2 stripe. So we've made things a bit better there. There's a bit of a simplification, but what we're doing now is we're reducing the metadata updates so that we don't actually have to write them to every single chunk, only the ones that are being updated. And I can very quickly show you some performance results. So these graphs are quite busy, but what we want to take away from this is we essentially want to compare like for like. So for example, the 4K on Squid versus the 4K on our prototype branch. And what we're looking for essentially is we're looking for the IOPS line to be longer so we get more IOPS before the latency shoots up and we hit the saturation point. So you can see from these graphs here that we're getting quite significant performance improvements for 4K and 8K in both random reads and random writes in this particular example. So yeah, we're hoping in the coming months we can get more of these optimizations merged into a prototype branch and get more performance results to show off. Yeah, that's everything I had. I know it's getting near the end of the conference, but I'll be here for another couple hours, and the guys from the UK will be here as well. If any of you guys can give a wave, just come and find us or find, yeah, they're there. Yeah, that's all I had. Thank you very much. I actually don't think there's another talk yet, so I can probably take questions, and then I won't be able to answer them, but Alex might. So maybe I should just give Alex a microphone. He can come down. I think Alex actually suggested that I include that in here, but I can only talk so fast, so. Yeah?
Does it matter which kind of erasure coding algorithm you use?
These should apply to all the algorithms and all the different types of erasure coding. Maybe not. LRC, maybe? Or yeah, yeah. One more? Yeah.
Is there any plan to apply RGW? So this thing works fine for RBD, but in RGW, if the objects are small and now they are striped object-based, is there any plan to move from object-based striping to common striping, like data pool, and the objects are just stuck there?
Before we came to Ceph, the answer was no. However, for the past 3 days, we've spoken to enough people who have said we need to optimize small lines. And what we realised we can do is we can put an optimization around, bypass most of the erasure coding, and actually use the erasure coding shards to write a m+1 replica. So it'll achieve the same level of redundancy, but without writing to all of the replicas. Also, as things that were not there, we're no longer padding objects. So even without that optimization, if you have a 4K object and you have 4 plus b, you'll still only write 3 copies.
So if you have 4K object at the moment,
The 4K
what we
object
do now is
you will lose.
it's going to be 24 kilobyte.
You'll lose 6. Sorry, you'll lose 6. Sorry, 4K, right?
So it's 24 kilobyte versus replica 3, which will check 12.
Still now accurate. But there's the encoding overhead. What we plan is getting rid of the encoding overhead.
Okay, thank you very much, guys.